And then we'll go over your assignment today. Oh yeah, before we start, actually, I wanted to start out with a little game. Okay, so every time we start class from now on, I'm going to start out with an interview question. The first person to get it right gets 5 points extra credit, right? Yay, woo! So you have to raise your hand to get this one, okay? You know it. Don't raise your hand if you don't know it. Actually, I should make you write it down on a piece of paper first. And then I'll come around and check it. So if you want to try to answer it, you have to write it down, right? Either on a piece of paper or on your computer, just so I can see your answer. So that way we're not shouting it out in case, you know. This is a good game. Good game. And no looking it up online. You're supposed to know this one. Because in an interview, then you're not going to be able to look it up. And so I just went to like different sites and I, got some questions. Or like students have told me interview questions. They come back and tell me what they were asked sometimes. We just have one today. Okay, I'll get some more as we go along. I guess I could ask some more. Okay, you guys ready? All right. Has to do with linked lists. All right. So you have to write down your answer and then I'll come around and check. Really easy, right? Are you joking? So if you get it, raise your hand and then you can show me your answer. You have to get all three. So it's just how many steps. So just think about like the worst case scenario. That's usually the right time. You got it? Okay, let's check. So for finding something, no. Almost. Except for deleting. And then another interview question would be, show how you insert something in a linked list. And they give you a whiteboard pen. Actually, that could be our next one. A lot of times they ask you questions, not in front of a computer, but in front of a whiteboard. Tell you the truth. And Google is famous for this, okay? They take you in a room with no computer, just a whiteboard. They hand you a whiteboard pen, and they start asking you questions, and you have to draw pictures. And they just want to see how your brain thinks, really, and make sure you know, like, simple algorithms. Okay? So just so you know, kind of give you a heads up. Almost. Except for the deleting one. Anybody else got it? Anyone want to take a guess? Okay. Just think about your steps, No. I even drew a picture, or I had a picture up here. I have a picture. Remember your linked list, your visual. Should we just, no one else wants to attempt? We had some close ones. Okay, how about for finding something in a linked list? So big O time means how many steps it takes. So worst case scenario. Worst case scenario, it's the last thing in your list. Okay, that's the worst case scenario, and that's usually how they do the big O time. Okay. Well, it is the average case, but then they get rid of constants, and it always ends up being the worst case, really. So just think about the worst case. Okay. So what's the worst case? The last thing in the list. How many steps does it take? So in here, n items is 4. There's 4 items. So let's say worst case scenario, it's the last item. So you always have to start at the head of a linked list. You can't jump to the middle of a linked list because remember, all you have is a pointer to the first item. So you have to start here. So that's 1. Goes to the next guy 2, next guy 3, next guy is 4, and you find it. So with n equal 4, how many steps it took? It took 4. So big O time for finding something in a linked list is n time. Okay. Best case scenario, it's 1. Worst case scenario, it's n. Average case scenario, n divided by 2. But they always get rid of the 1/2, the divided by 2. Okay? So it is n time. Okay, or big O n. You would write it, O n. O n time for finding something in a linked list. Inserting in a linked list, a couple people did okay. Okay. So when you insert something in a linked list, remember that this guy has a value and a pointer. Actually, I'll just follow their example here on my picture. So it's a simplified picture, but it's still the same. Okay, if I wanted to insert the number 4.5 right here, okay, I make a new link, call it 4.5, then what do? You take this pointer and point it here, and this pointer and point it here. That's considered one step. So a lot of times, even though, it looks like a couple steps, 02, but it's considered constant time, okay? And, it's considered one step. Of course, that doesn't include finding where it goes, but they're just saying the insert itself. And if you go look online, it's big O1 time for inserting something in a linked list. And remember, that's what made it advantageous over an ordered array, was that your insertion was O1. In an ordered array, how long did it take to insert something in an ordered array? Think about an ordered array. It's all, it's in memory all together. If I wanted to insert something in an ordered array, what do I have to do? Let's pretend this guy wasn't here. Right, I have to move everybody over. Worst case scenario, I want to insert something in the beginning of my list. What if I wanted to insert something in the beginning of my list? I have to move n items over. So inserting something in an ordered array takes big O n time. Or inserting something in an ordered linked list, O1 time. Okay. And then deleting something from a linked list. This is where a couple people Brian and Stephen had it right, except for the deleting one. So deleting something in a linked list, what do you have to do? Just change this pointer equal to that pointer, and voila, he's deleted. Remember, the garbage collector comes and gets him. So how many steps was that? 1. Usually you don't include the find. Just like in the insert, usually. If you included the find, actually you guys would be right. So maybe I should give you. Is that what you guys were doing, huh? If you include the find, then it would be ON, because then you have to find it first and then insert it. It would be ON plus 1, and then you get rid of the plus 1 because.
I was assuming like if you had that list and you said like delete the 5, I don't know which 5.
Yeah, you would have to find it. So that was pretty good that you guys saw that. But it does. It usually they'll, say it's O1 time because all you're doing is redirecting that pointer, and it just takes one step. And remember, that's why it was advantageous over an ordered array. Because what happens when you want to delete something in an ordered array? Worst case scenario, you want to delete this first guy. What happens when you want to delete it? You have to move everybody over. So how many items would you have to move over? N items over. So deleting something in an ordered array is big O n time. So ordered array, Inserting something in an ordered array? Good. And then finding something. Ordered array, we can use binary search. Finding something in an ordered array. This is where it was great. Binary search is awesome. What was his time? Yes, log in. Okay, that's where he's advantageous. And then deleting something in an ordered array. Yeah. So you guys should remember these for an ordered array and for a linked list. Remember, this is inserting. This was finding, inserting, deleting, finding, inserting, and deleting. You guys should memorize this. And if you don't memorize them, just visualize. Draw a picture. Okay? Even during an interview, they allow you to draw pictures. They probably like you to draw pictures because then they know you're visualizing. Okay? Than just standing up here blank. It'd be better to draw a picture. Okay? All right. So that was supposed to invigorate us for binary trees. Binary trees are cool. And the assignment for our binary trees, I have you guys make a game. Okay, so this should be, binary trees are pretty fun. So let's go over some terminology first and then look at some binary trees. So it's one of the more interesting data structures. It combines the advantages of the other two data structures, an ordered array and a linked list, which is why we just went over them. So you guys remember an ordered array and a linked list. So it's like the best of both worlds. Okay? You can search a tree quickly with a speed of a binary search in an ordered array. So binary tree search times are O log n. Okay, so searching something or finding something inside of a binary tree is log n time. Big O log n time. Pretty nice. Inserting and deleting items quickly. Okay, they can be an O1 time if it's a balanced binary tree. Okay, and deleting something in a binary tree is pretty much O1 time too. So it's the best of both worlds. Okay. In a lot of books, they always have this picture, so I stuck it in here. This is the common view of a tree, all right? And then this is the programmer's view of a tree. Notice it's upside down, okay? All right. Let's figure that out. Okay, a good example that we're familiar with is a file directory. Okay, remember that in a file directory, you can only go up to one place in your file. There's only one way to go up, but there could be multiple ways to go down. Okay, so that's a good kind of example. We'll come back to that one. All right, so here is a binary tree, a picture of a binary tree. And we're going to go over some of the terminology first. So that's a picture of a binary tree. The topmost node is where you start in a binary tree, and it's called your root. It's the only thing that you keep track of. Just like in a linked list, you only keep track of your first. In a binary tree, you keep track of your root. If you keep track of your root, you can get to all the other nodes. Okay? These nodes here represent your data. So the nodes encapsulate your data, and you can think of them as nodes like a linked list. They house your data and a pointer to another node. Actually, in a binary tree, you have 2 pointers to 2 nodes. Okay? The nodes that are on the bottom are called your leaves. Okay, so this is a leaf, and that's a leaf. Okay? When you draw binary trees, these are called your directed edges. Okay? It's a good example of a binary tree. Some more terminology. They call these children. And then this is his parent. So this is a child, and that's his parent. And when you look at code, a lot of times they'll code it like that. They'll call these guys the children and that the parent. He's a child and that's the parent. Notice that the root node is a parent to everybody. And a leaf is a parent to nobody. A leaf is always a child. Okay. Some more terminology. Sometimes they'll say that nodes that share parents are called siblings. Yes, they use family terminology, right? If a path exists from node P to node Q, so from a top node to like a parent node to a child node, then P is an ancestor of Q and Q is a descendant of P. So node with the number 2 is a ancestor of node 5. Node 5 is a descendant of node 6, node 7, and node 2. Does that make sense? Okay. The size of a node is the number of descendants it has, including itself. Okay. So let's see here. Nodes 2, 6, 5, and 11 are the descendants of 7. Node 7 is the ancestor of node 2, 6, 5, 11. Node 7 and 5 are siblings. All right. Cool. So that's just terminology. Oh, I forgot I had one more level of terminology. Because binary trees are pretty well used out there in the world, so there's a lot of terminology, right? A lot of people use different terms. Okay, the depth of a node, N, is the length of the path from the root to the node. And this comes into importance when we're making a balanced binary tree. Okay. So, let's see here. I have the levels spelled out here. Level 0, level 1, level 2, level 3. In a couple of books over here, they start at level 1 for some reason. Okay, but normally programmers like to start at 0, so this is a better picture, right? And the size of the tree is the total number of nodes in the tree. So what size is this tree? It has letters of the alphabet. You guys should be able to calculate that. Yeah, up to T. So 26 letters in the alphabet. Count down U, V, W, X, Y, Z. So size 20. All right. Okay, so how many nodes are in the tree? All right. And notice in a binary tree, each node can have at most 2 children. Okay. Oh, I forgot. Oh, well. In my PowerPoint, these were hidden, but that's okay. So which node is the root node? You guys should be able to answer that. It's node 8, right? It's the one on the top. Notice that this is an unbalanced tree, and it's not a binary tree. This is just a regular tree. There's different types of trees. Okay, there's red-black trees, binary trees, 2, 3, 4 trees. There's different types of trees. And here we just mainly focus on binary trees. Okay, and we have our homework with a type of binary tree. Okay. So name a leaf of the tree. The leaves of the tree are the nodes that are on the bottom. So that should be pretty easy for you to figure out. Node 4 has how many children? 1, right? He says 1 child. How many levels in this tree? There's 5, right? And there's 0 through 4. And the size of the tree is 11, because there's 11 nodes. Okay? All right. So, of course, binary trees, binary means 2, are trees where each node has at most 2 children. So here's some examples of some binary trees. These are all binary trees. More formal definition. And then binary trees always have a single root, always have a single path to every node, and it doesn't matter how we draw it. Is that a binary tree right there? Yeah, that's kind of a tricky, not well drawn binary tree, but it follows all the rules. Where's the root? Yeah, the second one. This would be the root, because no one, is pointing to him and he's pointing out. Every node is pointing to at least, or at most 2 nodes. Okay. And it has a single root. And every node can get accessed. All right, here's some more tricky pictures. Okay, it's the first box here. Is he a binary tree? How many people vote yes? How many people vote no? It is a binary tree. Do you guys see his root node? Yes, that second one from right, because no one's pointing to him, and every node is pointing to at least, or at most 2 nodes. How about the second one? That one right there. Yes. Okay, no. Okay, good. Yes, it is a no. Yeah, because 2 of them are pointing to the same node, and that goes against one of the rules. Okay, a node can only have, at most 1 other node pointing to him. Because when he's going up in the file path, you wouldn't know which way to go. Always think of it kind of like a file structure, right? That example. How about this one? It's a weird one. Does he follow all the rules? Yes, he does. Each node is pointing to at most 2 nodes. Yes, there's only 1. He's just the beginning of a binary tree, huh?
Doesn't that just make it a root?
Yeah, he's just a root. It's as if you only inserted 1 item into your binary tree. But he does follow all the rules. Okay, how about this guy? How many people vote yes? This is a tricky one. How many people vote no? Good. Yes, it is no, because you can't access this guy. So, oh, you thought it was 2? No. If it was 2 binary trees, then he'd be okay. But if he's a single binary tree, this guy can't be accessed because there's nobody pointing to him. You need an arrow, and then he'd be okay. And then how about this one? And no, that's not a mistake. How many people vote yes? How many people vote no? And actually, it is yes. And why is it yes? It follows all the rules. It's just an empty binary tree. Yeah, I like that one. Yeah, the root node's empty right now, so actually that's an empty tree. Oh yeah, I maybe, huh? But I like that one. That one's a good one. Okay. Okay, cool. Okay, let's talk about full and complete binary trees. Full and complete binary trees work very efficiently. Okay? Every non-leaf in a full binary tree has exactly 2 children. A complete binary tree is full to its next to last level. Leaves on the last level filled from left to right. The height of a binary tree with n nodes that is either complete or full is log base 2 of n plus 1. Okay? So these are your most efficient trees. If you can have a tree that looks like this, he'll work the best. Okay? All right. So let's look at a binary search tree. So a search tree organizes its data so that a search is more efficient. A binary search tree is a special type of binary tree where the nodes are in order. So binary search trees have to have nodes that contain comparable objects. Remember we did the comparable interface? That means nodes that have values that you can compare one to the other and figure out who's, greater than and who's less than. Like strings or integers or, right? A node's data is greater than the data. Okay, a node's data is greater than the data in that node's left subtree, and a node's data is less than the data in that node's right subtree. And a picture is worth 1,000 words, so let's get a picture. So here's a binary search tree. So notice in the root node, everything to the left of the root node is less than 8. And everything to the right of the root node is greater than 8. And when you look at every node, everything to the left is less than 4. Okay? There's nothing really to the right. If you look at number 19, 14 is less than 19, 27 is greater than 19. Okay, so a binary search tree, so you can actually almost think how you would search this thing. If you were searching for, let's say, the number 10, you'd look at number 8, you'd see that 10 is greater than 8, so you'd know you'd go down the right branch. Okay? You'd see that 10 was less than 19, you'd know you'd go down the left branch. You'd see it was less than 14, you would try to go down the left branch, see that it was null, and know that 10 was not in your tree. Okay? So just looking at that tree and knowing what you guys know, what is the search time? And we kind of already talked about, what's the search time for a binary search tree? Like a big O time? Each time we're cutting the number of nodes in half. So it would be log n. For a complete, full binary search tree, the optimum time is log n. Notice that for this tree, it'll be a little bit more than log n sometimes. Okay? When we search for these nodes down here, it'll be a little bit longer. So when it's not a balanced tree, it gets a little bit longer than log n. But a balanced tree, meaning it's full and complete, is log n. Okay? Dun, dun, dun. There's different types of binary search trees. Strings are comparable objects, so you could have a binary search tree of names, as long as the objects are comparable. Okay, so notice it's a binary search tree because everything to the left of the name that starts with a J starts with the letter that's in the before J, and everything that's to the right of the that name that starts with a J is a name that comes after J alphabetically. Okay, so you can have a binary search tree not just of numbers. As long as the objects are comparable, you can make it into a binary search tree. Okay? All right. So just like our other data structures, some functions of this type of data structure is to find something, insert something, delete something. And then another function of a binary search tree is to iterate through the tree or print the items in order. Okay? Or reverse order. Okay, so in your iteration, it'll have to do with traversing the tree or going through the tree. Iterating through the tree. Visiting all the nodes in the tree. All right, so let's look at our functions, and then we can look at our applet too. So you can almost think how these functions are going to work. So when you try to find something, you always start at the root. Okay, so you look to the root node. If the value is less than the root node, then look to the left. If the value is greater than the root node, then look to the right. Repeat steps 1 through 3 until the node is either found or the leaf is reached. That's your algorithm to find something in a binary tree. Pretty easy. Okay, let's look at an applet here. Yes, it's old school. All right. So I don't know, maybe I haven't looked lately, the past couple months, but we'll just use this guy. He's fine. So this is our applet to represent a binary tree. Okay, so he's representing a binary tree that has values of integer. If I wanted to find something in this tree, what number do we want to find? Okay, 67. All right. So let's say we're finding number 67. So you always start at the root node. Okay, so that's all you know is the root node. So is he going to go to the right or the left? Right. Good. Pretty easy, right? So he goes to the right. Okay. He compares it to 44. Which way is he going to go? Right. He's greater than 62. He'll go to the right. He's less than 69. He'll go to the left. And voila, we found him. Okay. Let's say we're looking for number 60. No, let's look for number 21. Something that's not in the tree. 21 is less than 31. It goes to the left. It's greater than 15, it goes to the right. It's less than 23, it goes to the left. It's greater than 19, it goes to the right. It's less than 20, it tries to go to the left, but what happens? It figures out that that's a null pointer, that he's a leaf, and he says, oh, it's not in there. So once you've reached a leaf and you haven't found it, it means it's not in there. Okay, should we look at the code for this at the same time? Okay, let's look at the code too. And I gave you guys this code too. So, well, actually this is my guessing game code. Let's look at this code and try to figure it out too. So just like linked list, we have a node class which encapsulates one of those round balls in our visual. Okay, so in our visual, a node is a circle. Okay, so the node is going to have some data stored inside of them. This node has two types of data, but the I data is like the key that's showing in the node in the circle. Just ignore the D data. He's just some extra data in there. It's just showing you that you can store more than one data item in a node. But your I data is like your key. And then it has two pointers that point to the left node and to the right node. Just like a linked list, we use that kind of logic. That he's creating an object of his same type as himself so he can point to other nodes. And they call it left child and right child in this code. Okay? Notice it doesn't have a constructor. Okay? Why doesn't it have a constructor in this code? Because it just constructs all your nodes to null, and then your I data is defaulted to 0. It's kind of messy code, but that's okay. All right? So that's your node. Here's your tree. Just like I promised, the tree only has one instance variable, and it is the root. So it only keeps track of the root. And root is of type node, of course, because that's the round ball at the top of the tree, right? All right. So let's look at our find. This is our find right here. This is it for find. Okay, so this is assuming that we have some items in the tree, okay? In fact, should we draw a picture as we do this? I was going to try to draw it in Excel, but we'll just draw it up here. Trees are circles. Circles are easy to draw. All right. So let's just draw a fast tree here. I already messed up. Let's put this as 5. 8 again. 9. 11. Okay, we'll have it look like that. That looks good. Just something simple. So here's our root. So we have something called current. Current will represent by a red arrow, just like we did in the applet. So here's our current. Okay. Current equals root. So he is a node pointer pointing to the root. So he's the root. Then we have a while loop here. While current's I data, which is the number 8, doesn't equal our key, which is what we're searching for. Which one should we search for? 11. Okay. We'll have our key. The parameter that we're passing in will be an argument of 11. This is what we're searching for. So while this I data, or the number in our ball doesn't equal our key, stay in this loop. Okay, so we check root. Okay, yeah, current I data is 8. 8 doesn't equal 11. We drop into the while loop. If key is less than current.I data, then that if statement will be true. But it's not, because 11 is not less than 8. Okay? So we do the else part. Current equals current.rightChild. Here's his right child. Okay? So do you see how he's going to equal the right child? We just moved current to point to the right child. If current equals null, it doesn't equal null yet, then return null, because that means we reached a leaf and we didn't find it. Okay? So we go back up in the while loop. If current.I data 9 doesn't equal 11, it doesn't, so we jump into the while loop. If key 11 is less than current.I data 9, 11 less than 9, that's false. So it goes to the else part, and current equals current.rightChild. So you equal this guy. Current doesn't equal null. Nope, he doesn't equal null. So we go back up in the while loop to do our Boolean check. Current.I data is 11. It doesn't equal 11. Does 11 not equal 11? That's false. That means, hey, we found it, and indeed we did. So we jump out of the while loop and we return current. So, hey, we found him, we're returning him. Okay. Now, I don't want to go through the whole thing again, but let's just assume we were looking for 12. 12 would still get to this point, too. And note that if we were in that while loop and it says current.I data 11 does not equal 12, which it doesn't, okay, it would go to that if statement. It would say 12 less than 11. Is 12 less than 11? False. It would say, go to the else statement. Current would equal current's right child. And what's current right child pointing to right now? He does have a right child, but it's pointing to null. So we've just set him to null. Okay. If current equals null, oh, that's true now. Then when we return null, means we never found him. Okay. Pretty easy code. Okay, you just have to keep track of what these things are visually, what's going on in there. Okay. But if you think about it, it's just like little arrows and, balls. That it makes sense how it was written, nice and simple. That's why binary trees are used a lot out there in the real world, because it is nice, simple, readable code. Not very complicated. And because of the great search find times and delete times, right? So you can kind of now see why it was O log n time, because each time we're jumping down a level in our tree. And for a perfectly balanced tree, it would be log base 2 of n to find something in the tree, or not find something in the tree. Okay? All right, let's look at the next function. Wait, not this guy. Which is our insert. Insert's still pretty easy. Here's our algorithm for our insert. To insert something, look for the node in the tree. If the node is already present, then don't insert it in the tree. If the node is not found, then insert the node into the tree where it should have been. I.e., the node will always be inserted as a leaf. Okay? You're always going to insert nodes as leaves in a binary tree. Okay. Let's look at the applet for that really quick. So we can start visualizing these things. Okay, so let's say we wanted to insert the number 21. We looked for number 21 last time. We figured out he should go at the bottom. I can go through this really fast because you guys should kind of know how he works? When you're inserting something into a binary tree, first you have to figure out if he's already in there and where he should go. So you traverse and look for him. So first you do your search. So when I insert him, he's going to search for the number 21. So he's going to go to 15, then he's going to go to the right. He's going to go to the left. He's going to go to the right. He's going to try to go to the right, but he can't go to the right. So he's going to insert him. Oh, you know what? I forgot. This applet only goes down 5 levels. Dang it. So let's insert something at the higher level. Let's insert something 24. Excellent. That's the detriment of this applet, right? So we'll insert number 24. He goes to the left. He goes to the right. He's going to try to go to the right, but it's empty. Wait. Oh, maybe if you don't push the buttons in the right order. Okay, there he goes. I must not have finished the other one, but he did indeed work. Applet's a little buggy sometimes. If I don't finish the other one, it didn't finish it. Okay, so notice it did insert the number 24 where it was supposed to be in the tree. Okay. Let's look at the code. Ooh, our code is kind of long. All right, so we'll start at the beginning of our code and then we'll work our way down here. So when you want to insert something into a binary tree, the first thing it does is make a new node and it inserts the data in the node. And make sure there's no, that the root isn't null, because that's its own special case. If your tree is completely empty, like that slide when it was just a blank slide, then you need to make the root node, that new node. So if you have an empty tree and you need to insert the root, that's a special case. Okay? Because otherwise you have to search the tree and this would return a null and then you'd have some problems. Okay, so if your tree is empty, then you make it the root node. Otherwise, you do this stuff. So if your tree is not empty, then you do the else part here. So let's go through it. Let's insert the number 12 again. Oh, no. Oh, yeah, so we were looking for the number 12. It wasn't there, so that's a good one to insert. We'll insert number 12. All right. So parent equals current. What does current equal? So we're going to have two pointers here. We're going to have parent and current. So parent will be blue and current will be red. Okay? And you have to understand this stuff to do your homework, this part, right? Okay? So current is equal to root. Right outside the while loop there, current is pointing to root. At the beginning of the while true loop, so notice it's a while true, parent equals current. So what is parent going to point to? The same node. Okay? If the ID, so that's what we're inserting is ID now. They didn't name it key, they named it ID. This is our new node. If the ID is less than current.idata, go left. So is 12 less than 8? Nope. So we're going to go to the else part. Okay. In fact, let me move this up a little bit. So we go to this else part. Current equals currents.writeChild. If current equals null, then we do that step. Does current equal null? No. Okay. Dang it. I need like a scroller. Oh, then we go back up into our while loop. So note that this was false because current doesn't equal null. It equals that node right here, number 9. So we go back up in the while loop. And what's the beginning of our while loop? Parent equals current. Parent equals current. We go to the if statement again. If the ID 12 is less than 9, then we'll go and do the if statement. Otherwise, we go to the else part. Current equals current.writeChild. Okay. And if current equals null, does current equal null? No. So we go back up in the while loop. Parent equals current. Okay. We check is 11, or is 12 less than 11? False. So we go to the else part. Current equals current's right child. U equal null. Okay. Actually, I shouldn't draw that in red. Can you guys see that? Because remember that he does have 2 children, but he's pointing to null. So now current's going to equal null. So this if statement's going to be true now. This is why we need parent. Parent.writeChild equals the new node. So here's our new node. Parent's right child equals that new node. And voila, he's in there. So do you guys see why you needed parent to follow along with him? Hopefully, yes. Okay, so you had to keep track of current and then also the parent so that when current equals null, you knew who he was before. Okay, it's a type of remembering. Yes. Okay, and that's how all the logic in tree works. Okay. Awesome. Now comes the fun part, the deleting. Okay, deleting's a little bit more complicated. This is where it gets fun. Finding stuff, that was easy. Inserting stuff, piece of cake, you insert it as a leaf. Okay, now deleting. Okay. Find the node in the tree. So you do your search. That was pretty easy. You find the node in the tree. If the node is not present, then of course you don't delete it. If the node is found and it's a leaf, how would you delete a leaf? If I want to delete, let's say 5, how would I delete leaf? Right, you keep track of parent. You keep track of current. What would I tell parent's right child to equal? Null. Garbage collector comes and gets him. Pretty easy. So if he's a leaf, it's pretty easy to delete him. You just delete the parent's, child. If the node is not a leaf, this is where it gets a little bit more, you have to think about it, but has a single child, then replace the node with that child. Such as, after I deleted number 5, he's no longer here. What if I want to delete number 4? He has a single child. I just replace 3 with 4. Or 4 with 3, sorry. I said that backwards. And then what do I do? And then make this guy null. And voila, that guy's deleted. Okay, so that's pretty easy. So if a node has 1 child, you just put the child up there. Voila, he's gone. Actually, I did write that wrong. So just note, see that it was 3 here, 4 here. I'll make it more proper here. So this was the parent. So when we look at our code, it'll look right? This is current. That's the one we want to delete. What exactly do? We take parent's pointer and point it to him, is exactly what we do. And that, in fact, moves that guy up the tree. So visually, he moves up the tree, but it's like we took this guy and we point him to the next guy. We take parent's left child and point it to current's left child. Okay? So when you look at the code, that's what that's going to do. Okay? What if it has 2 children? So I'm going to have to make this a little bit prettier now. Let's make them look better. Okay. So what if we wanted to delete number 5? If the node is not a leaf, and it has more than 1 child, so it has 2 children, then replace the node with its in-order successor. This is the right child's leftmost child. And if the right child does not have a leftmost child, then replace with the right child. All right, so if I was deleting number 5, who would I replace it with? 6, the right child. Okay, so think about how you would do that in the code. This would be current. Okay, this would be parent. How would I do that? You guys see? Parents.left child equals currents.right child. And then what else do I have to do? To make this right. Currents.left child now equals parents.right child's left child. Yeah, he points this guy to here, and then this guy goes away. So it's drawn kind of weird. That's why I had those pictures in the beginning, drawn kind of weird.
Do you have to make it current null if it's not pointed by anything else, or then you automatically get garbage collected?
Oh yeah, current at the end of this function gets garbage collected because he's only created in the function. So then nobody's pointing to him and he gets garbage collected. It doesn't matter that he's pointing to different people or different nodes. If no one's pointing to him, he's garbage collected. And current was created in that code, in the method. So when the method ends, current goes away. So that's why, you know. And so when you redraw it, 6 actually appears right here. Yeah. Like if I were to draw this prettier now, 5 is gone. And it's drawing sort of funky, but that's how he is. Okay? So when you look at your code, you know, draw pictures. Drawing pictures helps. Of current and parent. Okay? All right. Now let's do one that's a little bit harder. That was okay because he only had 1 right child. Okay. Let's say we want to delete the root. Number 8. He has more than 2 children. Oh wait, I need to draw a little bit better here. Well, this is a good case anyway. We'll do this case too. Then we'll draw them a little bit better. A couple more scenarios here. So who would I replace him with? The right child's leftmost child, and if the right child doesn't have a leftmost child, then replace with the right child. So who do I replace him with? 9, good. You guys knew it was 9? You were on track. Because notice that 8's right child is 9, and he doesn't have any children. Okay? So remember when we start those loops, current and parent are pointing to the same thing. And so we take current's right child equals parent's, current's right child, left child equals parent's left child. Okay? And then that guy's garbage collected. So it kind of did the same scenario. Okay, so current's right child equals, or right child's left child equals parent's left child. Okay? And then he's gone. Oh, and then in this case, we would now set root equal to that guy. All right. Now let me draw this prettier so we can do another one. We start getting ugly here. redraw him. Be 7. Let's make this a different number. Let's make it something big. 21. This could be 22, right? As long as it's bigger on the right. This guy could be something less than 20. This guy could be something less than 19. This guy has to be more than 19, but less than 20. Okay, we're going to make it a decimal. Okay. I messed up. We'll do 18 here and then 19 there. That's good. Okay, cool. Now we have a more complicated tree. Wait. Let's do a couple more, actually. Okay. Actually, we already have 20. 30. Okay. Make sure I'm right. Oh, wait. This would have to be... Dang it. Okay, hold on. Okay. That looks better. I need to use bigger numbers. Okay, there. That looks better, right? Okay, cool. Now let's say we wanted to delete number 30. Who would we replace him with? Good. Do you guys see that? So it's the right child's leftmost child. So he would replace him with 31. Okay, so abstractly, you're taking 31 and you're making this guy equal 31. And then you delete him down here. And notice that it keeps the correct order. Okay? What if I wanted to delete the root again? Say delete number 8. Who would I replace him with? Good. It would be number 10. The right child's leftmost child. So you always take the leaf here and then put him up there. So you take this 10 and you put him up here. See, after you get it, it's kind of fun, right? And notice that it always works. Because the right child's leftmost child is the least one over here. On this side, the right child's leftmost child is the smallest number, and that's what you're replacing him with. Okay? All right, cool. Cool. You guys want to do this one? So actually, I play a game. It's called the BST Challenge, Binary Search Tree Challenge. You guys want to try it? Okay, cool. I have to redraw my tree. All right. Or we could just leave him like this. Let's just add some more nodes to him. And we just like add and delete nodes. Actually, we could add a couple first. And we'll add them in different colors. Actually, I just noticed on this filming, it's not filming very good. I should have put them over here to begin with, huh? Okay, so who wants to come up here and be the first challenger? We can give away prizes. Okay, Justin, yay. And what should we have him do? Insert something? Well, we'll insert something first. Insert the number 8. So if you wanted to insert the number 8, and you can just put it in there. You don't have to go through the code steps. Like where would number 8 go? Yeah. Oh, he was actually going to do like the parent and the
Yeah.
parent. That was good. Good. Yes, you can drum in there. Awesome. Okay, cool. Easy schmeezy. Good. I should brought candy. Remind me next time I'll bring candy. You get. Oh, like dang it. We'll bring other stuff too. Okay. Who wants to insert the number 4? Where would number 4 go? Inserting's easy. Yeah, insert number 4. Yay. Good. Insert number 4. Good. Yes. Okay, easy. Now let's delete some stuff, right? Okay. And deleting is finding. Who wants to delete? Which one should we delete? Delete a leaf? Actually, let's go for a hard one. Let's delete number 31. Actually, that's too easy, right? Delete the root? Okay, let's delete the root. Who wants to delete number 10? I saw your hand go up. Oh. Okay, delete the number 10. Get stretching here. Yeah, the root. You guys can tell them what to do.
The rightmost, leftmost child. So 18.
Mm-hmm. But note that 18 has a child. We haven't done that one with a child yet.
So would be 18 still because we have the child to do. Oh no.
Okay, we'll just delete number 32. How would you delete number 32?
Just go straight across.
Yes, good. Excellent. Yeah, you can use any color. I don't care.
Well, you get the idea.
Uh-huh. But you can put the arrow there. You have to make the line. Okay. It's like a Band-Aid. What if we did want to delete the root? How would we delete the root? Which one would replace it first? Figure out which one would replace it. The 18. The 18 is going to go up there, but what happens to 19? It goes where 18 is. Good. Okay. So 18 gets put up here. So the right child's leftmost child. And then if it has a child, this guy points to that child. And do you see how it stays in order when you do that? Okay. All right. Not too bad, right? So you kind of have to think about it a little bit, but. Cool. We'll play him again next week. We'll remember what we did, and I'll have some more BST, some more binary search trees. Okay, so we'll play him again. Next time I'll bring some incentives, not just candy. Yeah, we should bring extra credit coupons and like little Easter eggs, right? That would be a challenge. People would actually want to play that. All right. So let's just go through iterations really quick. An iteration spits the values of the tree out. There are actually a few different ways to traverse a tree, not just one way to traverse a tree or iterate through a tree. And each traversal is going to list the values stored in the tree in a different order, of course. And there's a few different algorithms to do these different traversals, right? So when we traverse a tree, we can visit a node. And when we visit a node, we're processing the data in the node. So when we visit a node, it means that we're spitting out what's in the tree. Okay. A traversal can pass through a node without visiting it at that moment. And all binary tree traversals, regardless of the order that they visit the nodes, are linear with respect to the number of nodes in the tree, meaning that when you traverse a tree, what is the big O time in traversing a tree? You have to visit each node, big O n. So in every traversal, it's big O n time because you're visiting each node. Okay? All right. So here's a pre-order traversal. In pre-order, the visitation order of a pre-order traversal means that you're spitting out the node as you're at that node. Okay? So you visit the root before the subtree. So you're visiting number 1, then you visit number 2, and then visit number 3, and then 4, 5, 6, 7, 8, 9, 10, 11. In fact, I think in my applet, we can do a traversal. So here's an in-order traversal. Actually, we just looked at pre-order. But here's another one in order. And guess what in order does? It visits them in order. So notice it spits them out that they'll be in order. Okay? So an in-order traversal, it'll spit out. So it's not going to spit out number 31. Notice it starts on number 31, but it's not visiting the node at this moment. Okay? It's not going to spit out the number. It's going to go where? It's going to go all the way to the left, and then where? If it wants to put it in order, it's going to travel this way. Current's going to travel here, visit this node when it gets to a leaf. Go back up to the parent, visit that node. Go back down if this guy has a leaf, visit that, visit the parent. Visit this parent. Come down, visit this guy, visit the parent, visit this guy. So what's our algorithm? Go to the leftmost child, visit that child's parent. Go to the right child's leftmost child, visit that child, go to his parent. Yeah, it is recursive. In fact, we can even look at the code for that. Okay. So we can jump through it. You can see how it's working. And I put a link to this applet too. But the applet only visits in order. Okay. In fact, we could just jump to the code even. Now that you have a good idea of these trees, let's just look at the in order. We won't look at all the traversals. Let's just look at in order. So here is an in-order traversal of a tree. Look at that nice little code. How many lines of code is that? So note that binary trees is pretty simple, right? Remember that recursion is inefficient. Okay? But most binary trees are written with recursion because it makes sense. So note what it does. It comes here, it calls itself to go to the left child. It calls itself to go to the left child. It calls itself to go to the left child. When's the base case? When it's null. So it's when you reach that leaf. Okay? It'll come out here, it prints out that node. Then what does it do? It goes to the right child. It goes to the, and then goes to that right child's left child. Okay? But then it goes, that right child's left child. If that doesn't have a left child, then he, goes to the right child, and he goes around and around. Pretty much. All right. You guys kind of get it. But note that the 3 traversals we have written here all look the same, and what's different about them? So we have the pre-order, the in-order, and then we have the post-order. What's different? They're all pretty much the same except for one thing. When they visit the node, when they're printing out that node, when they visit the node. In pre-order, you print it out first, then you go to the left and the right child. And in order, you go to the left child, print him out or visit him, go to the right child. And in post order, you can kind of guess, you go to the left child, right child, and then you print him out. Okay, so those are the 3 traversals that we have. Okay, awesome. And I gave you guys this code. I think we'll save this part till next week, the deleting part, writing our code for the deletions. So when you're running this code, some of the deletions won't work till we write the code. Okay, but we can insert things. Okay, so note how this code works, and then you can show your tree. Okay, actually, in main, it had some default values. So if you look in main all the way down here, it inserted some stuff for us. Okay, and then it has a little menu system. So then it prints out our tree for us. It's kind of handy code. All right. And then we'll be writing some of those delete functions. We'll write a couple together, and then we'll write the algorithm for a couple next week. And then you guys will be in charge of writing some of them. All right. But I wanted to go over your assignment first. So we'll review deletions next week and write some of this code. Okay? All right. It is good code to write. And I think this is the end of my slides, pretty much. All right, just remember your big O times. Okay, so big O time in a binary tree takes O log n pretty much for everything. Okay, to insert, find, and delete things, it's O log n. So you can see that it's a better data structure than an ordered array. And it's a better data structure than a linked list. How big can a binary tree get? Is there a size limit on a binary tree? Anyone? No. Because it's just like a linked list, if we want to add more to a binary tree, we just make a new node and stick it in there. Okay, so no size limits. Why do we even have ordered arrays? Why don't we just use binary trees all the time? Why do you think we have ordered arrays instead of just binary trees all the time? How many of you want to code the delete functions for the binary tree? Oh, okay, so that's probably the biggest detriment for a binary tree. And yes, you could probably copy and paste some code. Okay, so just having that part maybe is a detriment to a binary tree. Ordered arrays are super easy to write. Okay, so, okay. And then just one last thing here before we kind of conclude today. Since we're thinking about trees. Oh yeah, this way, okay. So I'm making some new trees. Watch how the trees are made. What's wrong with this tree? This tree is not that bad. This tree is not that bad. Oh, this tree is horrible. Why is this tree so horrible? Everything on the right, this is an unbalanced tree. Okay, after you get off the right, actually it does stay balanced after you get off that right. But what made it unbalanced? Yeah, the 0. Why? Yeah, everything is bigger than 0. So note that if you choose your root badly, you will have guaranteed an unbalanced tree. Okay? So making the root something that's not really extreme. Here's another unbalanced tree. What's wrong with that root? It's really large. If we have numbers 0 to 100 and we choose root 93, we get another unbalanced tree. What's a good pick for our root? What would be the perfect pick for our root if we got completely random numbers? There's something in the middle like 50. Okay? So to avoid unbalanced trees, if I were inserting items in order, you would have O(n) time for finding. Let's say you inserted stuff in order. What would your tree look like? You could start to visualize your tree. If I insert items in order, so I'd inserted 0 first, and then I insert number 1, and then I insert number 2, and then I insert number 3. What happens to my binary tree? It becomes a, what does this binary tree look like? It looks like another data structure we all know and love. An array, but it also looks more like a linked list. It looks like an in-order linked list. So when you insert items in order in a binary tree, it becomes an in-order linked list. What if I inserted them in reverse order? Let's say we start with 100, and then we insert 99, and then we insert 98. It becomes a linked list on this side. So if you insert items in order or reverse order, it becomes a linked list. So what do we have to do with our binary tree? Pick a good root that's in the middle and insert items in random order. Okay, if they're random, then we have a nice balanced tree. If they're not in random order and they're just in order, we're going to have an unbalanced tree. You guys can see that, right? Or if you pick a really bad root, then you have an unbalanced tree. Okay? All right. I think that's a good place to stop right this part. I'm going to go over your guys' assignment for your tree assignment. So you guys can start it if you want. I gave you guys more than a week to do it. And we'll work some more on binary trees all next week. So Tuesday and Thursday we're going to work on some trees, and we can even work on this guessing game. Oh, dang it, and I forgot to attach it. Hold on. I don't know what I did. I don't know what I did. Hold on. So I've assigned this assignment before. It's a good assignment for a binary tree. It's not too complicated, but you do have to understand trees. So it's a good homework assignment. People usually like this assignment. It's really not that difficult, okay? Now this is a different type of binary tree. We're not going to create a binary search tree in this assignment, okay? We are using a binary tree, but it's not a binary search tree, okay? So for this assignment, we're going to make an animal guessing game using a binary tree. Notice it's not a binary search tree. I iterate again. People always go, whoa. We study binary search trees, but this assignment is just a regular old binary tree. That means a tree with 2 nodes each. It's simpler than writing something with a binary search tree. Okay? And it's fun. It's like a game. And this is how the game works. So let me play the game real quick. So the game has a little pop-up. Now you can use pop-up box or you can use console. I really don't care. Some people like to use the pop-up box. Okay? It says, think of an animal. I will try to guess it. Answer yes or no. Okay. So you press OK. Does it have 4 legs? I'm thinking of a horse. Of course. Yes, it has 4 legs. So we answer yes. Is it a dog? Nope. You won. Yay. What was your animal? A horse. Of course. Write a question that differentiates your animal from the animal I guessed. It would be yes for your animal. So it's a yes question for my animal. I'll put, does it eat hay? Or grass, we'll say grass. Or does it have hooves? Or does it have, something like that. A yes question for my animal. We press OK. And then we play the game again. Think of an animal. I will try to guess. I'm thinking of a horse again. Right, I'm building a binary tree. Does it have 4 legs? Yes. Does it eat grass? Oh, it remembered my question. Okay, I'll say yes. Is it a horse? Okay, I'm going to switch my answer because I'm cheating. I'm going to switch to a cow, so I'll say no. You won. What was your animal? A cow. Write a question for your animal. Do we eat it? Actually, people eat horses too, but does it make milk? Milk that we eat. Oh, that we buy in a store. Most people do not buy horse milk in a store. Okay, so then notice it ended. We play it again. Think of an animal. I'll try to guess it. Does it have 4 legs? Yes. Does it eat grass? Yes. Does it make milk that we buy in a store? Huh? Yeah, it could be a goat. So I'll think of a goat. Is it a cow? No. So note that it's building it's kind of like an artificial intelligent game. It's making a game for me. And the more I play it, the smarter it gets. It's like that Microsoft. Did you guys hear about the Microsoft artificial intelligent Twitter bot?
So this is like a miniature.
If you didn't, look it up. It's pretty funny.
So it's like a miniature.
It shows the mindset of our society. They taught it to say really bad things really fast. Yeah, look it up. Look up Microsoft Twitter bot. What was its name? Oh, well, just look up Microsoft Twitter bot. It's pretty funny. Okay? So it's like making an artificial intelligent game. It's kind of the same idea here.
Is it like a miniature 22?
Yeah, like a 20 questions kind of thing.
How many questions will this game ask?
Infinite. The more we play it, the more it will add to itself. If we play it 100 times, it'll ask 101 different questions.
So you can make it like an array, like it's like 20.
We're not going to use an array. You're going to use nodes and a binary tree to build it.
So like there's this web page called Cleverbot that like everyone can just go on there and start asking questions.
Oh, cool.
AI, so is that
Exactly.
online?
Yeah. Yeah, it's just building itself.
Can we limit?
AI uses binary trees. Search engines use binary trees.
Can we limit the questions like by limiting the number of branches?
You could if you wanted to, but in this one, we're not going to. It's pretty fun. And you don't have to do an animal guessing game. I could let you do any kind of guessing game. I really don't mind what kind of guessing game you do. Okay, I'll let you do whatever you want kind of guessing game. I don't mind. I just chose animals. Animals are easy. Everybody likes animals. All right. So I kind of go through it my directions. This is what it's going to look like. Okay? So when you first make him, it's just going to say, does it have 4 legs, and just have 2 answers. And then as you play it more, it'll have more answers and more questions. Okay, so note something about this game. All of the leaves are the answers. And all of the parent nodes have questions in them. So it's a very simple binary tree. Okay, all of your leaves are going to be your answers, or your animals if you do the animal guessing game. And all the non-leaves or the parents are going to have questions inside of them. But it still demonstrates we know how a tree works. We're building a tree. Okay. So it's like a simple tree, where the questions are in the parent nodes and the animals are in the leaf nodes. And for the question nodes, the answer to the left animal is always yes, and to the right animal, it's always no. So in this example here, the left animal has 4 legs. This is where I added that new question on. Does it eat grass? I added my horse, over here. Do I need to draw a picture of that? So like if I started out with this node, remember that when I was playing the game up here, I started out with that node. So this was 4 legs. And at first there was just a dog here. And I think over here I just put like a chicken or something. So when I first started my game, it looked like this. And when I answered yes, it knew it was a leaf and it said, oh, is it a dog? And I said no. It said enter a question about your animal. And what did I enter? Does it eat grass? Right? So how would I change this binary tree to make it work for my new one? Oh, and then I asked also what was your animal. Okay, so how would I place my node pointers? Right, this guy is going to point to the new question. This guy is going to point to the, the no answer. And this guy will point to the yes answer. And then what did I ask it? Or not what I asked it. What question did I answer? Or did I insert? Does it have milk, right, that you buy in a store? So we inserted that question. We changed this pointer to point to the new question. This points to the no answer. And this points to the yes answer. And then we store this binary tree. We make it serializable. Actually, I don't make you guys write that part, but if you want to, it's really easy. And we'll go over how to write that part. But when you serialize something, it deflates it, writes it to a file. So then when you play your game again, it opens, and there's your binary tree. Voila, he opens again. It's called serializable. Not cereal like you eat. Cereal like with an S. Okay. I'll even put the link to the API. It's really easy to make something serializable. It only takes like 4 steps. And it's good for us to learn this. We deflate our object, we write it to a file, we inflate our object. We read it from a file, inflate it. Okay. But yeah, we can make this game. Okay? All right. You can use the code I gave you to start with. Now note that you're not going to use your insert function that I gave you. You would just use the node part, and then you're going to have to write the rest of it. Okay? It's really not that bad. Okay? Once you get into it. And you have our other code as an example. Binary tree code is not that hard. Just remember that you have to have, a current and a parent. And you move current down, and parent will point to the parent. You'll make the while loops kind of the same way. Okay? And as long as you start it, I don't mind helping you, but you need to start it on your own. All right. Dun, dun, dun. Now, you can use dialog boxes or not. Some people like to use dialog boxes because it makes it more fun and interactive. Okay? But you could just use the console, too. I don't mind. I just thought, we're making a game. People always ask how to make the dialog boxes. It's not that hard. So I gave some examples here. Okay. Blah, blah, blah. All right. But the dialog boxes is optional. Okay, cool. Any questions on our assignment? All right, so it's not due next week. It's due the following Tuesday. So I give you all next week and we can even have some time at the end of class next week so if you start it this weekend, then I can help you a little bit, right? Okay, so to start thinking how you're going to code it, read your binary tree, search tree chapter. All right. If there's no questions, then that is all for today. So you have time to read also. And remember, hackathon this Saturday.